Hello? Okay, thank you. I had all kinds of problems today. I woke up on the wrong side of the bed, I guess. I woke up with a terrible headache, and then my internet was completely down. The server was down. And then I had problems with uh, putting my advertisement here on YouTube. Got some kind of error, so I don't even know if I didn't even know if I could communicate with you today. Fortunately, at least so far, I think I'm okay. Today, I think I stepped into the twilight zone or to the outer limits. Anyways, I'm going to start again with the fan mail. Okay, received quite a bit of it. And first one is administrative, more or less, okay. And someone asks, when and where will the next RS conference, the RSM, right, Rational Science Conference be? Well, that's uh, depends on the powers that be. Doesn't depend on me. We had the last one was in Sweden. My friend Martin. Organized it over there. Then this year we were going to have it. I think what was it, April or May? We were going to have it in Zambia. My friend Shamu was organizing it there, but it never happened. And I really feel so bad for him because he took a lot of effort to organize it for nothing. Then we had this COVID thing, and all the airports in the world were shut down. So I don't know when the next one's going to be or where because we got to wait till find out, what's going to happen. Right now, the world is shut down. And so there's a serious problem because we may be headed towards extinction faster than we are to normalization. For all I know, I mean, I don't know what the future may bring. I have no crystal ball. All I can tell you is what I think, and I think this is the beginning of the end. Exactly how long it's going to last, I don't know, but I think this was a severe shot in the foot for the global economy, which is the mechanism I propose for extinction. So, and I didn't expect it. I mean, you can't predict that there's going to be a virus that's going to, drive all the politicians crazy and they take all these decisions on locking people up and that kind of thing. So, I don't know. As far as I'm concerned right now, no one can leave the country, no one can come into the country, or, there are too many restrictions for a normal conference to take place. So the answer is I don't know. Okay. Okay, next comment. If I get this thing here. Universe, matter and space, definition of matter from Merriam Webster. It says substance of which a physical object is composed. Okay, we accuse the dictionaries of being of doing mereology. Okay, and so we don't agree with that definition. Okay, so let's go with the second one. Material substance that occupies space, has mass, and is composed predominantly of atoms consisting of proton, blah, 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 that constitute the observable universe and that is interconvertible with energy. No, that's not. That's why you shouldn't look up words in the dictionaries or scientific words in the dictionaries or in the encyclopedias. They do not have scientific definitions, not ones we're going to be using in science because they have no relation whatsoever to science. They all belong to common speech. Okay. I hope you can still hear me. Blank screen. Uh-oh, we're having problems. Yeah, I knew something was going to happen today. Excellent connection. Why don't I have image? Am I back or not? Please let me know if I'm back because I had all kinds of problems with YouTube today. Please confirm if you can see me and hear me. Yeah? Can you hear me and see me? I'm not sure what's going on with YouTube. I got an error message today. Okay, thank you. I, okay, thank you, Arthur. Appreciate it. I don't know what's going on today, but I foresee problems. I don't know what's going on with YouTube. I got an error from them. Right now, I'm not showing. Uh, well, just now I got again my screen back. Also, I was without a screen for a moment there as well. Okay, good. Let's continue here. Okay, where was I? Okay, so this fella asked about the definition of matter in space, okay, and about the universe. And so here's my answer to that. Okay, essentially, these are the foundations of physics. These are words that you must define, okay, for the purposes of physics. And specifically, I'm going to address the issue that he raised, which is universe. Okay, so I'm not going to put all the words that we need to define, just the pertinent ones. And the first thing we need to bow down to is the golden principle. Physics requires an object. You can't do physics without an object. Okay, that's a non-negotiable rule. Okay, you can't do physics without an object. And so these are the definitions. Object, that which has shape; space, that which doesn't; distance, separation between objects; and location, the set of distances. Okay, what does exist? Well, you have to have an object that has location. Okay, and so now we can move on to the two words that this fellow is asking: matter and universe. The first one is matter is objects that exist. You can say the set of objects, the collection of objects. In other words, all the objects out there in the universe, right, that exist, that have distance between them, and have location with respect to all others. In other words, under the rope model, if they're all interconnected by the rope, then they form part of matter. They are objects that exist. And universe is matter in space. Okay, so that means it includes all the objects and this thing which is not a thing, which we call space. Space is that which doesn't have shape. There you have the definition. And so all these objects are, you can say, contained within space. Okay, even though space is not a container. And I'm going to address that in a minute because someone asked a similar question along those lines. So I'll wait for that one. Okay, here's another question. I think this could be it, maybe. I don't know. Okay, he says, about space, we have no agreement on what exactly the word space means. First of all, in science, we do not agree. Okay, and we do not agree to disagree. Okay, in science, we got to get in the ring and fight for our definitions. Okay, and I hope you're still hearing me and seeing me. Okay. Please let me know. Put a comment if you can't hear me or see me because I foresee that something might happen. Okay. I don't know what's going on, but I'm hoping I can continue on with my presentation today. Okay. Anyways, the issue here is that we don't agree or disagree. We got to get in the ring and fight for our definitions. We are 8 billion people in this conference room, and all the doors are locked. No one can get out. No one can get out until we define the words. You can't say, well, I don't like your definition, I'm getting out of here. No, you can't get out. The doors are locked. Okay? You can't get out. You got to stay. You got to you got to fight for your definitions. Otherwise, you got to, okay, good, thanks. You got to fight for your definitions. That's how simple it is. If you've got a better definition, come on down and we'll argue, we'll fight, we'll put on the gloves, and we'll fight for those definitions. We do not agree, okay? Please do not agree with me. I hate it when people agree with me, okay? We agree on one thing, okay. However, that the space is a concept. Okay, space is a concept, but this definition must always be valid. That is, it cannot be both object and concept depending on the occasion. Okay, I agree. Okay, I agree. In other words, yeah, the word space is a concept. It means literally nothing. That's what it means, okay? That means that it's that which doesn't have shape. And so when we talk about an object, we have to put a background. And that background, that's what we call space, nothing, vacuum, whatever you want to call it. Whatever provides contrast to the object that we're interested in, the center of our attention, whatever provides contrast to that is not important. We call that space, nothing. Contrast, backdrop, stage, whatever you want to call it. Okay, so that's not the issue. The issue is not what's in the background. Okay, but we treat it as an object essentially because people ask, what's the black stuff there? And there is no black stuff. So it's not a stuff, meaning that you're right, it's a concept. Okay, it's a concept, and we simply have to use something as a backdrop. Otherwise, we wouldn't have the object. It would be an infinite object, meaning no object at all, if we didn't have some contrast. Okay, so yeah, we don't treat space is not an object, but you can say we can treat it as an object for the purposes of physics. If you want to say, well, it's something different than what's in the center, only in that sense. But no, it's a concept. So yeah, you're right. Okay. So how wrong can this association matter in space, which defines the universe, be? Well, it's not wrong or right because nothing is wrong or right. It's either rational or irrational. And if you've got a better definition or one that is rational, you got to put it forth, and then we all have fun tearing it to pieces. Okay, that's the way it works. Okay, in your hypothesis, the matter is threads and ropes. So consequently, the universe is. No, because again, universe is a concept. You can't say universe is this or universe is that. Matter, in other words, all the objects in the universe, that's what constitutes the objects. And then space provides the contour, the contrast. Okay, that's the way you got to look at it. And we call that whole shebang, we call it universe. Okay, so here's an object. Okay, and again, you don't pay attention to the black stuff. You can treat it as an object if that makes you feel better, but the object is what's in the center. The black stuff is just a contrast. We need that contrast in order to see the object. What is that object? Could be a blob, it could be X, Y, Z, you can call it whatever you want. Okay? But now there's contrast, now we can see an object. And it better not be moving. In fact, it can't be moving because it's the only object in the universe when you point to it. Can you point to space? No. The answer is no. You can't point to space. You say, well, I point to space every night. Here's the moon, and I point to what's next to it, that black stuff. Well, you can point to the moon, you can point to a tree, you can point to a dog, rock, house, whatever. You can't point to space because wherever you're pointing, I don't know what you're pointing to. What are you pointing to? Is it a what? Is it a thing? If it is, draw it for me. Illustrate that thing that you're pointing to. That way I'll know what you're pointing to. And you can't say, well, I'm pointing to that black stuff. Well, you got to draw it because there is no stuff that you're pointing to. That's the issue. You think you're pointing to a stuff, but you're not pointing to a stuff. You can point to the moon, you can point to the sun, you can't point to the black stuff because there is no stuff there. And if you believe otherwise, you got to tell me, you got to show me, especially illustrate what it is that you're pointing to. For that, you need to draw, illustrate space. Then we know it's a stuff and that you can point to it. You can't point to a concept. You can't point to nothing, which is what space is. So every time you say, well, I point to to space out there at night. You're talking ordinary speech. Okay? Let's get that clear. People have a hard time sometimes with these issues. Okay, another comment. Going fast through them here. Hopefully I'm not shut down yet. Okay, you have mistaken closed with isolated. He's referring to the closed universe, the closed system. Okay, so he's saying mistaking closed with isolated. How could something be contained without a container? You say the universe is contained by itself. Well, no, because first of all, there is no such thing as the universe. That's the first thing we got to clarify. Again, you're bringing ordinary speech, you're treating universe as a physical object, and you're saying that the universe is contained. Now, we have two ingredients in the word universe. One is the objects, in other words, matter, the collection of objects, whatever you want to call it. It's all those atoms there, maybe. Again, whatever you want to call it. That whole shebang, matter, we call it matter in general. That's one. That's half the equation. The other half is space, nothing. You have all these objects just changing their distances and their locations with respect to each other, not with respect to space, with respect to nothing. So here's the rundown. Okay, let's go through it. No such thing as the universe. Thing is that which has shape. So, the universe does not have shape. Okay. That's the first issue we need to clarify. The second one is universe is a concept. Concept, a word that invokes or embodies two objects or two words treated as objects, even though they may be concepts. Okay. Space is case in point. Universe, objects, and nothing. Okay. Where nothing is treated momentarily as something. Backdrop, if you wish. You can, if you're smart, you don't even have to do that. You can say it's just a concept. It's nothing. Therefore, the universe is not something, and the universe is not and cannot be physically contained. Okay, so we're talking about matter, not universe. Let's get that part straight first. Unlike in ordinary speech, okay, objects are contained by the mere fact of the definition of nothing. Nothing, that which doesn't have shape. So the objects in the universe, in other words, the objects that exist, matter, it cannot escape space because there is no boundary, no perimeter, no line that you can cross. Okay, you can't build a Trump wall and escape to the other side because there is no other side. There is no wall to space. Okay, that no surface, no boundary, no perimeter, whatever you want to call it. Okay, and objects cannot escape that which doesn't have shape. Okay, so if it doesn't have shape, matter is trapped simply because it has nowhere to go. Okay, that's the issue. Now, let me rub that in a little more because it's important. A lot of flat earthers, especially, and there are other people, especially people who propose particles in general, and they propose that everything is done through pressure. Okay? Now, why do they say that? They say that because they never discovered the force of pull. So here we have a universe, okay, where all atoms, all stars, all galaxies are physically interconnected. They're not pressurized from the outside by particles or by whatever, and they're not in a container. They are in space, which is that which doesn't have shape, which doesn't have boundaries, okay? So they're trapped not because something is squashing them, but because every bit of matter is pulled towards every other bit of matter. That's the situation here, okay? Let me check real quick, see if we're still, I hope I'm still connected. Let me know with a comment if I get cut off. I'll be checking every so often. Anyways, all these atoms, all these stars, all these galaxies, whatever you want to see that as, they're all physically interconnected. So there is no pressure from the outside pushing galaxies, stars, or anything else, atoms, together. Okay? The way it is that everything is pulled inwards. Okay? And you might say, well, if it's all pulled inwards, shouldn't all that collapse in a single stone or somewhere in the center after gazillions of years? Okay, thank you. Um, the universe, or in other words, matter in the universe, could be rotating. Okay? Now, the way I've illustrated this, everything is rotating in the same direction, everything is rotating clockwise. You could have parts of this rotating in one direction, another one in another. They could be clockwise, counterclockwise, or 90 degrees to that clockwise. All the matter, all the galaxies, everything that's out there in the universe could be moving in different directions, completely in different directions. And that's what prevents, in fact, Newton said this is not mine, by the way. Newton said that, that's what prevents all the matter clumping somewhere in the center. And essentially what Newton predicted, you could say, is galaxies, okay? Because galaxies are chunks of matter, gazillions of stars that are clumped in what we call galaxies. So they're stuck in these island universes, which are connected to us. How do we know? Well, because the light reaches us. And how does light travel? It travels through the rope, the electromagnetic rope. So all the atoms in the Andromeda galaxy are connected to every atom in your eye. Okay? Every rope from every atom in the Andromeda galaxy is connected to your eye. That's why you can see the Andromeda galaxy. Okay, do we understand that? So Andromeda is connected to, physically connected to the Milky Way. Okay, every atom is interconnected from atoms here to every atom over there. Okay, and Andromeda, in fact, is approaching us according to the astronomers. It's 2.2 million light years away, but it's coming in our direction. And there could be other galaxies that are moving in opposite direction because they belong to another, what is called the local group. Okay, so no, the universe, I cannot imagine how it will clump together in a single stone someday in the future. I don't know. I think the universe, I see it as eternal in both directions of time. Never had a beginning, will never have an end. If you come back a trillion years from now, you'll see the same thing. You'll see galaxies, stars, atoms, just floating out there in what? In nothingness. All you have is atoms with respect to atoms, stars with respect to stars, and galaxies with respect to galaxies. That's our universe. That's our simple, very simple universe. Mathematicians have made it real complicated by putting ghosts and goblins called dark matter and dark energy and talking about Big Bang and parallel universes and other nonsense. They have no idea what they're talking about. Okay. No, our universe is very simple. It's just matter. That's it. And what is complicated is how matter turned into life, us. That's an interesting part. Okay, so let's question here or comment. Let's see what this one's about. Fellow says, circle and triangle are 3D and not 2D. Okay, I got to revise all my geometry now. Has X, Y, and Z dimensions. Okay, I challenge you to draw a 2D anything. Okay, so how do we reply? Okay, here it is in a nutshell. Okay. First drawing is neither the criterion nor the test for 2D or 3D. Okay, you don't draw a 2D. That's one issue. The other issue is you can't draw or make an ideal 3D cube. That one down at the bottom is a two-dimensional 3D cube. In other words, it's a projection. And what you do next after, because that's an ideal cube, remember. I can show you let me push this aside for a second just to show you this. Where do I have it? Where is it? Jesus. Oh, here it is. That's a cube, right? More or less, but it's not a perfect cube. No, I can't substitute this for an ideal cube. Okay, the Rubik's cube, it's not a cube. Okay, it's partitioned into pieces. It's got nooks and crevices, and so no, that's not an ideal cube. Okay, an ideal cube is smooth, perfectly smooth, and can only be illustrated in two dimensions. Does that mean it's not three-dimensional? No, it's three-dimensional because you later on have to describe it. You have to describe it so the person understands what he's staring at. And he's staring at what, a cube, which is a two-dimensional version of a cube, but with the description, you're supposed to see depth in there and see it as a 3D entity that can only be projected onto a 2D platform. Okay. Tribar, which is that little triangle down at the bottom, well, that's, you can't draw or make, you can't make that. You can draw it on 2D, you can't draw it in 3D for sure. And the other issue is whatever you draw is physically 3D because it is made of atoms. Okay. In other words, if you take a pen, a chalk, a crayon, whatever you draw is going to be 3D. They just disconnected me. Am I still alive? I hope so. They just disconnected me. I have no idea what's going on with YouTube. Okay. Momentarily disconnected. Maybe I'm back. They say I'm back. I hope so. Let me know if not. Okay. Anyways, you can't make a tribar. And then there's this confusion in confusing the fact that the ink is 3D and the paper, okay, thank you. The paper is 3D, but what we're doing here is putting an image and describing it as 2D, okay? So you're confusing the ink and the paper with the circle and the triangle. Circle and triangle are 2D because that's the description we give to the thing that you drew. Okay? And you should not say, okay, I'm going to test you and see if you can draw it. No, of course you can't draw a 2D image in a 3D world. Everything is 3D, even every drop of ink and every piece of paper. So you're confusing the actual paper and ink with the circle and the plane. The circle and the plane are 2D because they're described, the image is described as 2D. Okay? So you should not confuse drawing with the notion of what a triangle and a circle are, or square. And finally, I can just say that conceptually, planes are faces of solids. What is a square? It's a face of a cube. Can you draw a cube? No. You can't make a cube, not a perfect cube. It's going to be 3D. It's going to have surface. You can make it as perfect as you want, but it won't be perfect because when you go in there with your SEM or your atomic force microscope, you're going to see the atoms. The crystal lattice will not be perfectly smooth. Absolutely not. So even the plane called a square will not be even though it's a face of a cube, will not be 2D in real life. Okay? So again, we should not confuse the real life with what the image is supposed to be. All planes are 2D. They don't have depth because that's the description you give that figure. Okay? That's the way you can use it in geometry. Okay, moving on here, another comment. Okay, fellow says, what did he say? I don't yet have a definition for object that excludes 2D, and you would be hard-pressed to find one. You will never find any other definition than the one that I made. I'm sure I've broken my head on it. I consider it my biggest contribution to science, the definition of the word object, not the rope. My contribution is the word object. No one in 10,000 years figured out how important that word was to physics, and therefore no one defined it scientifically. A couple people had, Aristotle and Euclid, they mentioned in passing, oh yeah, figure is, Euclid defined figure as form, okay? But first of all, he never used that. He always used itineraries. That's the first issue. The second one is no one even noticed that definition, how important it was. So no one ever used it. Even to this day, no one in mathematical physics uses the notion of figure because in mathematical physics, they don't use objects. So they talk about itineraries, always. Everything is in motion in mathematical physics. There is no static thing or no object, or only mathematical objects, as they call them, which are all dynamic objects. What does that mean? That means that, they can't put a true, genuine object in an equation. They can't put the word dog in there, or they can't put a dog in there. No, they have to put a value, a quantity, an amount. That's why they don't have objects in mathematics. And these are the people who are, supposedly interpreting the universe for us, the physical universe. And they don't have objects. They want to do it all with math, with descriptions. That's where the problem is, okay? Okay, so here's my answer to that. Essentially, the golden rule or principle of physics, physics requires an object, and I'm saying the scientific definition of the word object destroys all religions, okay? Uh, no religion survives the word object. It's the word object everybody's going to have problems with. First of all, because everybody thinks it's that which you can see or touch. No, it's that which has shape. We don't need a second object to do the seeing and the touching. That's the main point, okay? But that takes us to people, to not people, but objects such as God. Is God an object or a concept? I asked people in Aberdeen, Muslims. We went out to dinner together with a group that we met over there, and they were Palestinians. And I just asked them one question and it drove them nuts. I said, is God an object or a concept? That's all I want to know. And boy, I had all kinds of answers. First, that God was both. Another guy said that if I knew what God was, then he wouldn't be so great. They give you all these runarounds. They can't tell you whether God is an object or a concept. So here we cut through the BS. Okay, here it is. Okay, if God is a concept, he doesn't exist by definition, because only objects may be said to exist in physics. Okay, and if God is an object, that's not enough. He could be a 2D object, a cardboard God, in which case he does not exist also by definition. No 2D object exists, can be said to exist, okay? And even if he's 3D, it doesn't make him exist automatically, because that could be the God that I'm dreaming about, that I prayed to in my mind, and that God doesn't exist. If God wants to exist, he's got to be out there, and the way we show that God exists, he's got to have distance and location. In other words, there's got to be a distance between God and me and every object in the universe. Otherwise, God doesn't exist. Okay, so God has to pass a lot of hurdles before he can exist. First, he can't be a concept, then he can't be a 2D object, and then he's got to have location as well. So those definitions are important if we want to eliminate atheists and theists and agnostics from the record. All these people talk about belief and knowledge and about running a test and touching and seeing. It's no. In science, we define the word exist and the word object, and then we know whether God exists or not. Just follow the definition and you won't get hurt. Okay, very simple. And what applies to God also applies to general relativity. Here's the hypercube. Well, what you see there is an object. It's a 3D object projected onto 2D. What is hypercube about it? I don't know. I mean, do you see anything other than a 3D ice cube inside another ice cube? That's all I see. Okay, so that's 3D. There's nothing 4D about that. Okay, so it's a 3D object, no problem there, and it's projected onto a 2D platform or background. That's fine also. Okay, that's an object. Space-time. If that's supposed to be space-time, we got a problem, because space-time is a concept. Time for sure is a concept, okay? Right? I mean, I can't point to time. I can't bring it to the conference and say, here's time, right? What am I going to bring? A clock? Or what is it, an atomic clock? No, time is a concept. And so if there's a unification between nothing, which is what space is, and time, another concept, well, nothing and time does not make an object. So yeah, the definition of the word object destroys relativity, okay, and destroys the black hole, because if black hole wants to be an object, all that the black hole has to do is have shape. And what is the shape of a zero-dimensional singularity? Okay, that's the issue. And yeah, a lot of people are not aware that Chandrasekhar proved that a black hole is zero dimensional, zero volume, zero size, and that's what he got the Nobel Prize for. Okay, so let's get that all straight. Some people out there think that, well, no, it just shrinks to a little ball. No, no, that's not what the religion of general relativity says. That's the first issue. The second one is, why would it stop at a ball, at a marble? Why doesn't it continue squashing until all matter is, uh, what is it, crushed out of existence, as they say, right? So why would it stop at a little marble? Why do you think it stops at a little marble? Why doesn't it continue crunching matter until there's nothing left except mass, a concept, weight? Okay? Yeah, mass is weight, weight is mass. And a lot of people have a hard time understanding that. And that's a long story. Okay, let's move on here. Another issue brought on by this fella. In bgaede's version of the multiverse, God could possibly exist, but would have no way of interacting with his clump of tangled ropes we're a part of. Not to mention, it's got some fancy language here, okay? Not to mention the fact that he couldn't possibly have created it in the first place, but could only have ever pushed the ropes and atoms around, which would be tough since he'd be blind to them as we'd be blind to him. And that's an interesting statement. I think he said it quite well. Okay, and here let me tell you what this fellow is talking about. Okay, I try to illustrate what this fellow mentioned here. Here's God, and there's the universe. Okay, if God wants to see you, wants to see the universe, if you want to see God, if the universe wants to see God, there had better be connections between God and the universe, because under the rope model, light is what carries light. The rope is what carries light, to use that terminology. Essentially, there's torsion going from one atom to the other. That means God would have to be made of atoms. He can be made of whatever he wants to be made of. But if he wants to communicate with us through sight, through vision, through light, he's got to be connected to my eyes, just like Andromeda is. In other words, every part of his body, he could be made of sophisticated stuff, heavenly stuff that I don't know about. That's fine. But the only way I can see him, the only way he can see me, is if he's connected through ropes to us. Okay. And so the issue is he's got to be connected. And here's I made the other day a little video also here. You can see three universes, okay? And the ones on the top are connected by electromagnetic ropes. I just put three. We can imagine them as gazillions, okay? And those two universes, if they're connected, they belong to a single universe, okay? Because there's no reason for them to be isolated. They are connected through the electromagnetic ropes, okay? But what happens to that third universe at the bottom? If it's not connected to us, or to this other universe that's connected to us, right? We can't see this universe. We can't see it because we can only see through the electromagnetic ropes. In other words, the electromagnetic ropes are what brings the image of that atom in the other universe to our eyes. If that universe is not connected to us through electromagnetic ropes, we can't see that universe. And be interesting if that universe came towards us, we probably wouldn't see it, but the question is whether we would collide. So if one day someone shows up in your room and breaks through your door and you can't see anything, well, that spirit, that's probably a guy from another universe that just crashed into ours. But see, the point here is that all atoms have to be connected. And the same with God. If God wants to be part of our universe, he's got to be connected to us. Otherwise, he's in a parallel universe. We can't see him. He can't see us either. So I don't know what the point is to have that God there, you know. Maybe he works through the mind. I don't know. He can't influence me in any old way if he's not connected to me. He's got to be physically connected, for otherwise you are using black magic. Okay. Okay, let's continue on here. Another issue. So then, because DNA is a rational explanation, well, DNA is not an explanation, it's a hypothesis, an assumption. You make an assumption, say, with DNA, I'm going to explain such and such thing. Okay, whatever. It's an example of rational science outside of physics. It's within science. Physics is part of science. So there's only one science. We call it rational science to distinguish it from those people who do religion and supernatural and irrational explanations. Those do not belong to science. Whatever's rational belongs to science. So I'm not sure what this fellow is referring to. Can the same thing be said for meteorology in regards to pressure and current as explanations? Yeah, I mean, again, meteorology is a branch of physics. Okay, we're done. So, and physics is a branch of science. So, again, we're done. Okay, if one were to come up with an alternative explanation for the weather, so long as it wasn't magic, would that be rational meteorology, theoretical meteorology? No, it would be meteorology only. That's part of science. That's it. We don't have to qualify it as rational or theoretical because science had better be rational. And theoretical, all science is theoretical. The purpose of science is to be rational and explanation. Okay, so I don't know if I'm getting through with that. Anyways, what we do in science is we define science first because we need to know what the subject matter is, and we define it as rational explanations. There's only two branches. One is physics, the other one is philosophy. Okay, here we deal with physics, which is objects, causes, and mechanisms. And that's the rational scientific method. It's the way you get an explanation to a listener. Okay, and you present a hypothesis which includes the object's definitions and the initial scene or statement of the facts. A theory, an explanation, mechanisms and causes, that's what you're going to be explaining, again, for the purposes of physics, and then your interpretations and corollaries. Okay, that's typically the way we present a theory to someone else. Okay, and science is 150% qualitatively. We use no numbers, equations, math. Why? Because those can only describe, and science is not about describing, about measuring, about calculating, about making predictions, or about observing. Gawking, drooling. We don't do that in science. What we do in science, we explain. That shows that you used your brain. Okay. Okay, another issue here. Lots of questions brought up. Lots of people want to know. Okay, charge is the aggregate of friction of the electron balloon. How does an effect entirely localized on the surface of the atom affect anything at a distance? Okay, what does it even mean for friction equal charge? Friction is friction. Where is the push-pull? Is it in the reeling action of the pulsing that causes the friction in the first place? Does a negatively charged surface just have more electron friction and less for positively charged, or what? Where is the action at a distance of electron friction charge? Okay, some of these issues we have not resolved. Okay. Saying this up front. Okay, so especially static electricity, big problem still. Okay, we're trying to visualize what's happening in there. One possibility that I'm at least considering, I'm still analyzing this issue, is that static electricity, because static means it's going to stick to something. It could be magnetism. Okay, a different way of doing magnetism, because you're rubbing, what you're doing is aligning a row or a series of atoms or molecules, and then suddenly you have something twirling there, which are the electromagnetic threads, and when they twirl they can latch onto something. So one of the things I'm looking into, I'm not saying I've got a final thing on this, so I can't answer some of these questions, okay, is that static electricity is maybe a form of magnetism. Okay, that's one issue. The other issue is that, as far as the charge on the electron, which is what we're trying to visualize here, I do have a explanation for that of what it is on the electron. And part of the problem here comes because people associate the word charge with numbers. For example, 1.6 times 10 to the minus 19 coulomb is the charge on the electron. That's what they've come up with over the years, right? And that's what they use because they need that number in an equation. So people associate charge, the word charge, with that number. And so when I talk to people about, interpreting physically what charge is, people are lost because they're thinking mathematically and not physically. So that's part of the problem, okay? And so I can go back and ask you the same question, say, what is charge from a physical point of view under quantum mechanics? That's what you got to answer, okay? And of course, you won't find the answer because what you'll find is math. And that's the problem. That's part of the problem that you've got here. You can't associate it with friction and other things. But here it is, okay? This is our version of what charge is, okay? Essentially, the atom pumps back and forth and doing its quantum jump. And right at the surface, you can see that it swallows and releases one link of the rope, okay? And the aggregate of that friction going on in there, what is friction? Maybe some kind of rubbing, the going back and forth of the shell. That's what we call charge. That's what we've measured when we came up with the 1.6 times 10 to the minus 19 coulombs, okay? So we're trying to give a physical interpretation to what charge is. And people who have been, educated to be mathematicians, they have a hard time relating to that notion because they're thinking mathematically. They're not thinking physically. That's the issue. Okay, so you got to get into your physical mindset and say, look, what are we visualizing? What's happening in that secret world of Mother Nature's? That's what we're trying to illustrate here. But again, a couple of those questions, I have no answers yet. And all we can do is continue trying to elucidate what's happening in that invisible world of Mother Nature's. Okay, here's another question or issue. Goes into space with a sand clock. He's talking about gravitational time dilation. Sand floats all around inside the clock. Oh no, time is non-existent out here. Einstein was right. Okay, so makes a little fun of me. Okay, fine, no problem. Here's my answer. Here's my answer to him. Okay. Is this any better? Goes into space with an atomic clock. Runs slower around an irrational concept called the black hole singularity. Oh no, my twin brother back on Earth is 50 years older than me. Time has stretched like a bubble gum. Warp time is what prevents the Earth from flying out of the solar system. Yeah, Einstein was irrational, okay? So I'd rather be wrong and not irrational. Okay? So let's keep that in mind. Here's a sand clock. We turn it around, and what does it do? Well, you can see what it's doing there. It's going around, falling. The grains are falling to the bottom floor. Okay, there you see it. Okay. Okay, so what is the issue there? The issue is that a sand clock, hourglass, is a gravitational clock. It works only because of gravity. And yes, in the middle of space, there is no gravity and the grains don't fall. There is no time according to the clock. Okay? Is the atomic clock any better? No, because when you take it out there, according to general relativity, it slows down. Okay? Depending. Well, if it's gravitational times dilation, it speeds up. And the one down here is the one that slows down. But when you take it for a ride, like around the black hole and then come back, the twin paradox, then the clock slows down. Okay, so is that any more accurate than this one that doesn't measure time at all? I mean, can you trust that clock if it slows down or speeds up depending on gravitational or this dynamic relativistic time dilation? So what's the point of a clock if you can't trust it? But there is a clock that we can trust, okay? At least for the time humans are going to be on Earth. Um, and that is the Earth orbit around the sun. That was our first clock. It was a calendar, okay? We used it to define the word year and later on months, weeks, etc. But, to test the twin paradox is very easy. We throw all clocks away except the orbit of the Earth around the sun. That's the definition of 1 year. Okay? Now the twin can go at any speed he wants. He can go at tachyon speed and just beat the speed of light, come back, turn on his head, whatever he wants. When he comes back to meet his twin brother left on Earth, all we have to do is count the number of times the Earth went around the sun to know how many years went by. Anyone who's got a number different than that has got an irrational clock, a clock that needs tweaking, that needs fixing, mending. Okay? So the Earth is our clock for the word year. You can't tell me that you're going to measure with an atomic clock seconds, to determine how many years went by for the twin that went out on a trip close to the speed of light. Okay, and yeah, we don't put gazillions of candles, one per every second of your life, on the cake. We just put the number of candles according to how many revolutions the Earth made around the sun. That is an objective standard. That's the one we use. And so now the twin can go at any speed he wants, come back, and we don't care what special relativity says. There had better be 50, 40, or 30, or whatever number of orbits of the Earth around the sun when they both meet again. Okay? Very simple test. Okay? We don't need all these other nonsense that NASA and the other relativists use out there to calculate how many moons went by. Okay, I think it's the last issue here. Lots of them today, okay? Um, the force of gravity increases because the actual number of ropes increases. You have the example of the astronaut being pulled down to Earth, etc. It is the actual number of effective ropes which causes gravity to be more or less intense. Yeah, correct. Okay, I'll illustrate that in a second. Question, why is there no change in gravity during the rotation of the Earth against the sun, or is there? Okay, here it is. Let's go first with let's illustrate the first issue there, and that's this one here. So get it up here, okay? If the astronaut is farther away from Earth, all the ropes come together and you have gravity is weak. Okay, as the astronaut approaches the Earth, the ropes fan out, and that is the physical interpretation of the acceleration of gravity. Okay, I hope that's clear. What you have is what we call effective ropes. That means that the ropes are no longer on the same axis because the atoms are not on the same axis. Okay, and as you approach the Earth, as two objects approach each other, the ropes fan out. Okay, so that's the explanation or physical interpretation of the mechanism of the acceleration of gravity. Now for the second issue, why doesn't the gravity change? Okay, here's the Earth going around the sun. And essentially, here I have it going around as a circle. But remember that the sun moves around the center of the Milky Way. So that explains why Kepler's laws are applicable. In other words, that you don't have a perfect circle, but you have these ellipses for every planet. And what it is essentially is that, yeah, gravity changes so slightly only when the Earth is farther away and closer to the sun. But other than that, essentially, it maintains the same gravity because, as an average, the distance is more or less. If you treat the orbit of the Earth as a circle, essentially there wouldn't be any change in gravity other than the imperfections of the surface of the Earth. You got Mount Everest, you got sea level, that sort of thing. So the gravity would change very so lightly. Okay, but other than that, no, the Earth essentially has the same gravity at all times because it's this. This is the mechanism. You swing the ball around, okay, and uh, and that's what it is. If my fingers here are the sun, this is the Earth going around the sun, and since it more or less has the same distance from the sun in general, as an average, then you can say, yeah, the gravity of the Earth is more or less the same. Do you change your weight with respect to the sun every time the Earth goes farther away, in that elliptical orbit and closer to the sun? Yeah, of course. You change your weight with respect to the sun, right? The Earth, in that sense, does change its weight, which is what gravity is. Okay, gravity is weight, and what is weight? Location. Location. Why? Because the number of ropes changes according to location. Okay, that gives you the idea of what gravity is, and it fits perfectly with Newton's equation. Keep in mind that Einstein's equation is something different. Okay, he changed the mechanism. Einstein's equation says that there is a point mass. Okay, going around the sun. Could be, Venus. He did it with Mercury, okay, because that was a big issue. There's a point mass going around the sun. And what the equation does, the field equation does essentially is calculate the orbit of the point mass. That's different than saying, I let go of the spoon, it falls to Earth. What pulled it down there? Well, it's mass divided by distance squared. That's Newton's equation. You can't do that with Einstein's equation. You cannot explain with Einstein's equation why the fork or the spoon that you let go falls to the center of the Earth. Partly because Einstein's equation only works at the cosmic level. That's why they can't blend quantum mechanics with general relativity. Okay, so keep that in mind. There's a different. See, that's how they came up with warp space. Because instead of saying that the point mass is moving around like this ball around the string, right? Instead of saying that, they said, oh, space is curved, and the planet, in this case Mercury, is following the curvature of space. So what the field equation does essentially describes the curvature of space, and whether it's a photon or a planet, it follows that contour because it has no other choice but to fall around the sun. Okay, so it's a different physical interpretation and a different equation than Newton's equation, which says mass divided by distance squared. Okay, I hope you understood that. You need to understand the differences of what changed in 1915 when Einstein came up with his general relativity. Okay, let's move on to Mr. Jim Al-Khalili's. Here we go. Okay, well, he starts out talking about the atom, and he says the following. He says, we asked where we had come from, how were the stars created, how all the elements were made, even how the universe itself had begun. One of mankind's greatest achievements is that we've answered these questions. Have we? Are you satisfied with those answers is the question, okay? Are they rational, okay? As we peered inwards, we realized we could explain what we saw when we peered outwards, okay? So he's talking about peering into the atom as well as peering out into the cosmos, okay? The atom has helped us solve the greatest mysteries of existence. Oh, has it? I don't think it answered any mathematical physics. It hasn't answered a single issue of existence. So what he's bragging about, I don't know. It's false advertising as far as I'm concerned. Okay, so let's move on here. He says, he continues on with his lecture or presentation. He says, here we have Atom Man. I hope I'm still, okay, I hope I'm still in communication. I'll check every now and then there. Okay. Everything in the world we see is made of out of tiny objects called atoms, and yet we've only proved their existence at the beginning of the 20th century. Prove their existence? What is he talking about? You don't prove existence. What do they prove? God, the existence of God. Do you prove space-time? How do you prove these things? And he's talking about proving the existence. Amazingly, we now have a pretty good idea of the number of atoms in the universe. This is a mind-numbingly huge number. It's one followed by over 70 zeros. That's a trillion, 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 trillion atoms. So these people say they know how many atoms there are in the universe. First of all, I think it's a waste of time what they've done. But second, are they correct? Do they have a one with 70 zeros atoms out there, or is this absolute poppycock? And then you have the issue of they talk about the observable universe. And they say they calculate that. How can they calculate that when they're telling us that there are virtual particles, positrons and electrons, that pop into existence momentarily? Maybe they participate in some, because they have to show what they're used for. I mean, if they just pop into existence and then back out, who cares? But no, they use the virtual particle very heavily to explain things of why something happened in the lab. That means these virtual particles don't go back into space. They participate actively in our real world. That's what these people are saying. So should we consider those electrons that pop in as being, part of atoms? I mean, were they part of atoms when they were part of space? I mean, we got a problem here. These electrons are just flying around and suddenly they pop in for no reason. They separate. You have an electron here just flying around. We have more electrons in the universe suddenly. And then it goes back into or out of existence. I mean, how can they count the number of atoms if maybe there are more atoms that make up space? Do they have anti-atoms out there in space? Together with atoms and anti-atoms, and so not only do electrons and positrons pop into existence, but maybe the atom itself pops into existence, in which case we cannot know how many atoms there are in the universe. What nonsense is this about saying how many atoms there are in the universe? How about all the atoms we can't see, all those gases we've got out there? Can you really estimate that? What we do in rational science is we say, look, there's a bunch of stuff out there. How's that for accuracy? Okay? It's not important how many atoms there are in the universe. I don't think even God took the trouble to count them all. Poor God, I mean, his computer must be burning if he counts all those atoms. Okay, anyways, these people say that they counted all the atoms in the universe. That's great. And then he continues on. He says, it's an astonishing, let me get this down here. It's an astonishing human achievement that we now know not only how many atoms there are in the universe, but why they exist at all. They know why the atoms exist. Okay. We can now explain how those trillion atoms were created. We're talking about God creation here. They were created? Created from what? It turns out that the mystery of creation itself lies within the heart of each and every atom in the universe. Yeah, have no doubts about it, make no bones about it. General relativity, mathematical physics, is a religion, and they believe in creation. They do use the word creation. They talk about creating matter because that's what they think they do. They think they're creating matter from nothing. What do they call that nothing? They call it energy. What is energy? A concept. What is a concept? Nothing. Okay, you got it? I hope you got the full circle there. Okay, so yeah, there is no... Okay, I hope I'm still connected here. So yeah, there's that issue of where did all this matter come from? Well, that's what we're going to answer here. Or Jim Al-Khalili is going to answer this. He begins with a history, okay, of the atom, and he just goes through here. This is a summary. Curie discovers radium, I think 1896-97. Scientists became alchemists. The first one was Rutherford. And what he did, he put radium in a jar of ordinary air and produced hydrogen gas. He eventually figured out that N2 morphs into O2 and H2. There was your H2 gas in the presence of radium. Radium apparently did something to these gases, broke them apart, and created hydrogen gas. Okay, and he explained the different elements as different number of protons. Okay, that was good. I love that on Rutherford. Okay, he's got a he needs to get a kudo on. Okay. However, he couldn't explain weight. That's not my statement. That's Al-Khalili's statement. Okay, because he couldn't explain how helium is supposed to be equal to two hydrogen atoms because it's supposed to have two protons, and instead it has four hydrogen atoms in it, and it has the weight of four hydrogen atoms. Okay, in fact, not quite as well either there. But the issue is that until Chadwick, 12 years later, 1931, proposes the neutron, they had no idea why, especially helium, was not mass of two. Instead, it had closer to four. And they couldn't explain that until they figured out that, oh, helium has a couple neutrons in there, no charge, but has the weight, okay, atomic weight. Okay, but protons don't push each other away inside the nucleus. So you have two positive charges, okay? So if these are your two protons, okay? If they're both positive, they should push away. And that means the atom should explode, the nucleus, right? And that didn't happen spontaneously. So they said, uh-oh, we got a problem here. And that's when they went into La La Land. Okay, they started going into crazy, inventing ever more nonsense from that point on. They had to explain why protons don't push protons away. And now, yeah, now I recommend that you go get a beer because it's going to get rough, okay, for the mind, okay? What happened? Well, let's get it up here. What we had is that, at least what Al-Khalili explains, he says, if I put some Velcro around these magnets, you know, you have two magnets and they push each other away because positive repels positive. Well, if you put Velcro there, you know, that yellow stuff, now you put them together close enough and they'll stick together. Well, no kidding. Okay, so at first they repel each other just as before, but when they get close enough, the Velcro kicks in and they stick. The effect is very short range, but very, very strong. In other words, it overpowers the magnetic repulsion, and it overpowers gravity. It overpowers everything. This force, this Velcro that's in there. So we need to figure out what that Velcro is. And it's exactly the same with protons. The strong nuclear force explains what holds the nucleus together. He's saying that Velcro is the strong nuclear force. And he says it's only felt down a distance of a trillionth of a millimeter. In other words, you got to get them close enough for that Velcro stuff to bring the two magnets together, the two protons together, for them to stick. Okay? Now, is that a sound explanation? Well, absolutely not. And here, let me show you why. Okay, I'll illustrate it first, then I'll explain. Okay, here's why not. Okay, here's Velcro under SEM, under high magnification. And you can see that it's got these hooks when you look at it in magnification. And that's why Velcro sticks to things. Okay, Velcro to Velcro and Velcro to carpets and to whatever. Why? Because it's got these hooks. So now, what is the hook in the analogy with respect to quantum mechanics, with respect to the proton? Are they saying that the proton is coated with some kind of Velcro that has hooks and Velcro pulls on Velcro, and that's why you can't separate these two protons? In other words, they don't illustrate, they try to explain with an analogy saying, well, imagine it's like Velcro. You get it close together and then you can't separate them. Yeah, I can understand the analogy. What does that have to do with proton and proton attraction? And they're saying, well, it's like that. Okay, illustrate it for me. Because what you're going to have to illustrate the Velcro on the surface of the proton first, and then you got to show me how the Velcro sticks to the proton to begin with. Okay, so you see where we're going with all this. We got a physical problem. I don't care about their math. I don't care about their measurements. None of that matters. Here we're trying to figure out what is happening in Mother Nature's secret world. And if he's going to use an analogy, he's going to say, well, we explain it with Velcro. Okay, fine. What's the analogy has to serve a purpose. And if Velcro attracts Velcro, what is the Velcro of the subatomic world? And how does that Velcro stick to the proton in the first place? Those are the questions. Okay, and here we have an answer from one fellow. Okay, his name was Yukawa. Hideki Yukawa. He was a Nobel Prize winner. Okay, all these people get Nobel Prizes what? For doing math. Okay, and what does this fellow say? He says, in one of the protons, an energetic gluon spontaneously creates a down quark and an anti-down quark pair. Okay, let's go slowly here so you understand what's going on. Creates a down quark, okay, and an anti-down quark pair. Next, the pion, okay, drifts, that's another particle, okay, drifts into the other proton, okay, it's going to drift over there, okay, and the anti-down quark annihilates with a down quark, okay. It's like positive annihilates with negative, okay, they neutralize each other, leaving the other down quark to take its place. So the issue here is they're saying, look, people will probably understand it more with charge because people are more familiar with charge. Imagine there's a positive charge over here and a positive charge over here. Okay, we got two positive charges. Okay, so what we do, we take a gluon, a couple gluons, they go out there and they turn magically because you can only do this with magic. You turn those two gluons into into a positive and a negative charge. Okay. So the negative charge over here, one of those two negative charges, neutralizes the proton or the quark that was positive, the positive charge, and the other one takes its place, and now you have positive against negative, now you have attraction. So they explained this mathematically of why, of how there's attraction because north attracts south. That's it, or positive, negative. They have no explanation. What they say is, oh, we've got the mechanism. The mechanism is you neutralize the positive charge that was repulsing the positive charge over here, okay? And you turn that into a negative charge by doing this gluon fancy footwork. Now you have a negative charge, now they attract. All they're telling you is positive attracts negative. They haven't explained physically what's going on. They said, oh, we just have to show that positive attracts negative. And they go through this rigmarole of changing the polarities. That's essentially what they're doing. They're doing it with down quarks, up quarks, anti-quarks, all that nonsense, or gluons. But that's essentially the mechanism that these people are explaining. They're saying, look, you just have to change the polarity, and then you have attraction. But still, even with balls, you cannot explain why a negative ball attracts a positive ball unless you can illustrate the physical mechanism. And that's where they introduced the velcro, the little hooks there. Okay, why? Because they can't visualize what's going on in there with particles. With particles, that's the key predicate there. Okay. Okay, he continues on, and here we see how they get into little trouble, okay? Because what? With a strong nuclear force, humans finally began to get a glimpse of what was actually going on inside the atomic nucleus, did they? Roughly speaking, all nuclear behavior is down to a balance between the strong nuclear force squashing, see, he used the word squashing, the protons and neutrons together and the electric charge on the protons forcing them apart. What these guys are saying, they're using the word squashing because they're suggesting there's some kind of pressure. It's not called squashing. It's called pulling. It's not a question of pressure from the outside. It's the pull from within. That's how Velcro works. Velcro is a pull from within, but see, they use the word squashing. They fit these things in there. He's going to use later on the word squeezing again. They talk about squishing and squishing and squashing and squeezing when they should be talking about pulling, but they can't use the word pull in quantum mechanics because there is no mechanism of pull in all of quantum mechanics, and there never will be. You can't pull with particles. That's the issue. That's the problem. That's why these people can't answer these questions, and that's why in the end they always say, we don't understand this universe. Of course you don't. Not with particles, because you cannot explain it with particles. But see, that's what he uses, that word squashing. Okay? Protons and neutrons together and the electric charge on the proton forcing them apart. Okay, so let's continue here. Um, Al-Khalili moves on, and he says the following, going on with strong force. And here it is. You can see it. What they use, those are gluons, those bed springs that you see there. Those are gluons. And what kind of particle is that? Have you ever seen that in the standard model? You'll see the word gluon in there, and they give you some numbers about mass and charge and other nonsense, irrelevant nonsense. But at no point do you ever see a picture of any of those particles. Specifically, you will not see this bed spring. Where are these bed springs when you need them? I mean, I can understand the analogy there, but I don't see the bed springs in the standard model. That's where I have a problem with that. The analogy is inconsistent with the standard model. That's the question. That's the issue. Okay. Okay, and here's just a look at the atom under that model. You have this is the hydrogen atom. Okay, you have an electron going around three quarks that are being held together by bed springs known as gluons. Okay, and of course when you ask them, well, what do you mean bed springs? What are those bed springs? Well, that's when they'll give you some math gibberish. They can't justify the bed springs. That's the issue. They can't justify pull, and they're going to talk about what? Squeezing and squashing. Okay. So they use this fancy footwork in their language, and they mislead you. So if you're not in tune with the language, you're going to have problems, because they're going to trick you just with the language. They're going to say, oh yeah, it's squeezed together, squashed together. What do you mean squeezed and squashed? I thought you were talking about pulling, Velcro, Velcro pulls, it doesn't push. Okay, here he tried to make sense, so I put good old Al-Khalili back in his regular image. Okay, how does the sun shine? Good question. Hey, the nucleus of a single atom of hydrogen consists of just a proton, and every now and again inside the high pressure, high temperature cauldron of the sun, this proton can get squeezed. Again, squeezed, not pulled, but squeezed up close to another. See how they trick the language? They're no longer talking about Velcro or using that analogy. It's not pulled or preventing from separation because you got a hook there. No, it's now squeezed together, squashed together. That's how they trick you with the language. And bang, the strong nuclear force kicks in and fuses them together. Again, fuses. The strong force is like coming from the outside, not from the within side, okay? Because they can't explain the force of pull. Keep that in mind. That's the issue. Hydrogen fusing again. That's why they call it fusion, right? Fusing into helium, and the energy released is what we see and feel as sunshine. Now that's strange that he would say that, because the first thing he does is go in there and beat up on Fred Hoyle, okay, who suggested that the elements were created in stars, such as the sun. And there was a big debate between Hoyle and another fellow. His name was George Gamow. And it's George Gamow who's going to lead us into the Big Bang. Okay, if ever you heard of the Big Bang, well, now you're going to know why, how that came about. How did we come up with this nonsense of the Big Bang? Okay, here it is. Let's work on that. Fred Hoyle, he was trying to say the following. Okay, he was saying that essentially, right, that the elements, 92 elements, I guess he was referring to all 92, were created in stars. Okay. Fred Hoyle explained how elements are created in the stars. Supernovas create heavier elements. You need big explosions, big pressures, etc., big heat, and you get them in supernovas. Okay. One glaring problem, one that Hoyle, this is what Al-Khalili says, okay, that Hoyle could never explain away. Stellar nuclear fusion can't explain how all the elements in the universe are made except for two, hydrogen and helium. In other words, they say they cannot explain those two elements. This was the issue. And Hoyle had no answer for this, okay? To have the amount of helium the sun would have to be burning at billions of degrees, but the truth was that the sun only burned at millions of degrees. You needed billions and you only had millions. That was the issue. The sun just wasn't hot enough to have made all the helium we know that it contains. We got a problem because it turns out that the sun turns hydrogen to helium. I mean, even babies know that, okay, today. That's the theory. You may not agree with it, but I mean, that is the theory. That's the reigning theory, that hydrogen is turned into helium through a fusion process. Here he's saying that we don't know where all the helium came from. Hydrogen was turned into helium. Period. We're done. And here you see a just one uh, piece of evidence. You'll find it all over the internet. I just collected one because, I mean, you'll see it all over the place. And it says the most important reaction within the core of the sun is the process called proton-proton cycle. Hydrogen nuclei are converted to helium nuclei through a number of intermediates. Okay, and they go through that process, and it says nuclear fusion, the source of all the energy so generously radiated by the sun, does two things. Okay, converts hydrogen into helium. We're done. Okay, and rather makes helium nuclei from protons, and it converts mass to energy. Okay, blah blah blah. And there's the reference. So we already are aware that the theory says that hydrogen is converted into helium, but here Al-Khalili denies it or questions it, says it couldn't have made all that helium. Why not? He doesn't explain that. He just says it couldn't, and so he sides with this other fellow, George Gamow, and this guy proposes something else. He proposes that all that. And here it is. Okay, did you get the beer as I asked you to? Okay, here it is. He says that all this happened in the Big Bang, a few minutes after the Big Bang. Okay, if all the helium wasn't made in the sun, then where did it come from? Where did hydrogen come from? Was the universe created in a single instant, or had it always been there? And those two questions are all, or the three questions are all related. Why? Because again, George Gamow, and here, let's get this, get it down here. He goes in there and he says, "Oh, I know where it's all created. It's all the same question." He says, "Here it is." And the question is, that we created all this in the Big Bang. And by that time, they had developed the notion that all galaxies are going farther apart. That means in the past they were closer together. When you put them 14 billion years ago, at that time, that's when time was created. That's when the universe came to be. And in a few minutes after the Big Bang, that's when helium and hydrogen were created. That's the origin of helium and hydrogen. Of course, Fred Hoyle didn't like that because he was an atheist, and he said, this smacks at religion, creation. That's what we have today. We have creation. Okay, so if mathematical physicists tell you that theirs is not a creationist theory, they're lying or they're ignorant. Mathematical physics, Big Bang is a creationist theory, and they had to use Big Bang to show why we have hydrogen and helium today so much in the universe. 98% of the universe is hydrogen and helium, and so that's why they had to bring Big Bang. That's why they're not going to let go of that religion, because otherwise, their whole edifice collapses. So they can never deny the Big Bang. That's why they hold on so strongly to it. Okay. Okay. So what have we learned from Mr. Al-Khalili? Here's a summary. Okay. If I can get it up here. Okay, so what did we learn? Here it is, a summary. Atoms answer all questions. That's how he starts his presentation. Protons held together by velcro-like particles. Absolute nonsense. No relation between the analogy that he uses and the standard model. Nowhere in quantum will you find the hooks needed to simulate Velcro, or Velcro simulating the protons. Aside from the fact that you got to stick the Velcro to the proton to begin with. If this Velcro is a little particle, how does it stick to? Does it have glue on its surface and it sticks to the proton? Yeah, this has got to be answered if you're going to give a physical interpretation. Sun shines because protons squeeze together. No. If Velcro is the analogy, then they should be pulled together, not squeezed or pushed or pressured together. Okay. Sun can't produce all the helium. Okay, I don't know where he got that because the sun is producing helium as we speak, according to the theory. It doesn't mean you have to believe it. Again, this is not a question of belief. It's a question that is the reigning theory. And Al-Khalili is aware of it. So he can't deny it and say, oh, we don't know where the helium came from. What do you mean you don't know? Hydrogen is being converted into helium by the sun. If he doesn't like the quantity because he believes that the sun can't create so much quantity, which they say up to a quarter of the sun is helium, whether it's true or not, I don't know. That's also a guesstimate. We've never peered inside the sun, for one. But then the other issue is, even assuming that were true, we don't know how long the sun's been around. Okay, they say 5 billion years. We don't know. Those are guesstimates. And one guy has one opinion, another guy has another opinion. And again, it's whatever you want to believe, whatever assumptions you want to make. So there's nothing ground in stone that says the sun has 25% of its material be helium, one, and second, that we don't know where it came from. And then he concludes that Hoyle was wrong, that you cannot do this just by supernovas or regular star-like activity. You need the Big Bang. You need a big, enormous explosion. That would create hydrogen and helium, according to them. And that justifies why we have Big Bang. And it was proven by Arno Penzias and Robert Wilson when they discovered the background radiation. Okay, in, 1963. They had their antennas. They were trying to get rid of noise. They couldn't get rid of that noise. They found it was the 3 degree Kelvin background radiation from the original Big Bang, or at least that's what they say it is. Take it or leave it. I'll see you on, on Sunday. We'll see you then. Bye-bye.